Hi guys. We're gonna do spectrometer right now with our experimental
Wait,
our unknown.
this is probably not. Do it on the table where they're safe.
Unknown 720. Nice. Right.
So we took our 3 solutions for microcolumn chromatography and put them into separate beakers. We had the stock solution, fluorescein, and methylene blue. We took 3 cuvettes, 1 for each, and a clean pipette for each, and pipetted each solution into its assigned cuvette and filled it to the line. This is us walking to the spectrophotometer room. And our TA decided to be a furry today, but he let us in.
Did you get all that? Oh my gosh.
So we start by opening up the scan app. That takes forever to load, but it's worth it. It's kind of fun to watch. So you clean 2 sides of your cuvette of the blank and you put it in the spectrophotometer and you make sure that the clean sides are the one that the light's going through. And you close it and mark it, or you zero it. Then you start and mark the graph. So you're going to take out each cuvette and put in the next one of each solution.
When scanning across all wavelengths, the spectrum shows various peaks where absorption or emission occurs. The highest peak in the spectrum corresponds to the Lambda Max, which shows where the substance absorbs the most light. 2 examples of why we would scan across all wavelengths are chemical analysis and materials, because scanning across all wavelengths allows us to identify an unknown substance or the concentration of the substance, and finding the materials helps us analyze the optimal properties of these materials.
Alrighty, y'all. So absorbance is directly proportional to concentration, and this linear relationship basically allows for determining unknown concentrations by measuring the absorbance and the calibration curve. So failing to zero out this machine with a blank would affect absorbance value by not accounting for possible background absorbance, and it can lead to inaccurate estimation and errors.
Oh yeah, I mean like, y'all are like moving way faster than other things.
Thanks!
Yeah.
Alrighty, y'all. So the Beer-Lambert law is basically the amount of radiation a substance absorbs, and it's equal to the extinction coefficient times the path length times the concentration through the dilution calculations. And here we are basically cleaning. So you can see we're using soap and water. We've dumped all of our solutions in the waste container. Yeah, see, this is great. We're just really doing a lot of cleaning here. Lots of cleaning.
I just wanna be part of your symphony.
What? Not enough for you? Do you want more?
I just wanna be part of your symphony. We'll be tired and not let go.
There you go. I hope that was enough sympathy for you.
So we're basically ending up our cleaning with drying off the beakers, putting them away. We're having a great time. Yeah, as you can see. Ooh. Anyway, we're wiping down the tables and we're doing our math calculations. So the RF value is what we're calculating right now. And this is basically the distance traveled by a component over the distance traveled by the solvent. So you're dividing the two. And it is a value without units. This value indicates the preference of the solutes for the stationary or the mobile phase. So that's what we're calculating right now. So basically we're calculating the distance traveled by each of our components by subtracting the endpoint minus the starting point, and we're dividing that by the distance traveled by the solvent. And these were our final results.
Well, this lab definitely took a lot out of us. This was us before the lab class started, and this was us after we finished our lab. So yeah, definitely a grand old time, but thank you guys for watching.
Yay.